Hi guys. In homework one part C, we talked about thermal resistance, and today we're gonna dive deeper into the difference between series and parallel resistance and how to derive their expressions. So first, we're gonna differentiate series pathway and parallel pathway. So series is when heat travels in one path through multiple layers. And then parallel is when heat travels through multiple uh, multiple paths at the same time. So like we know before in series, heat transfer due to energy conservation, all the Q are going to be the same. So Q is equal to Q1 equal to Q2 equal to Q3, blah blah blah. However, since in parallel heat or divided and travel through different ways. We can have Q equal to um, heat path number one plus path number two plus path number three. So Q is like Q total. And then we can have a different expression for thermal resistance as well. So for series, R total is going to be equal to R1 plus R2 plus R3, etc. And then for parallel, it's gonna be 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus etc. So we're gonna explore what how to derive this expression. Okay. So now we're gonna start with series. Okay, I'm gonna draw from somewhat we did in homework C. It's gonna be in a similar scenario where we have um, 4 different layers. First one is coffee, and then we have glass, and then insulator, and then air. So we can have tea, coffee, um, T3, T2, T1, and then T air. So we're gonna write the general heat equation by conduction, or general heat transfer equation. So we have Q. We're gonna write the general heat transfer equation. So we can have Q is equal to delta T over R. So delta T is the driving force, and then R total is the total resistance in the system, and then just heat. So we're gonna write this equation for each of these different uh, Q individually. Okay, so Q, general Q, we have Q is equal to T coffee minus T3 over the resistance of coffee, and then, or the resistance by convection of coffee is equal to T3 minus T2 over the resistance of glass equal to T2 minus T1 over the resistance of insulator. And then finally we have T1 minus T air, which is the resistance of air. So we discussed in homework part C that resistance R is equal to So it depends on if it's by convection or conduction. So you know that by conduction, R is equal to length over Ka. So length over thermal conductivity times area, and then by convection, we have resistance equal to 1 over HA, heat transfer constant. So now we're gonna write each of these equations individually. So I'm gonna go to a different. Q is equal to T coffee minus T3 over R um, or coffee. And then we have Q, we have Q is equal to, or actually, let's move it this way. Q, R, coffee. We're just gonna move resistance to the other side. T coffee minus T3, and then continue. We have R glass. R glass is equal to T3 minus T2, and then Q or insulator is equal to T2 minus T1, and then Q or air is equal to Q T1 minus T air. So you see this over here, if you plus all of these QR coffee, QR glass, QR insulator, and QR air together, we would be able to cancel out T3, T3, T2, T1. This one is T air, my mistake. So we would just cancel this out, cancel this, and cancel this. So we would have, let me just scroll down. We would have Q, R coffee, R glass plus R insulator plus R to the air is equal to T coffee minus T air. And then so you see that like the equation we have above. Also I forgot to mention, so in series Q are all the same, like we talked about above. So that's why we have these equation equalities. But anyways, so see up here we have Q total equal to R total is equal to R1 plus R2 plus R3 for a series. So these together would be equal to R total is equal to delta T, and then we have Q times. So that's how we derive the expression for uh for series. And now we're gonna move on to parallel.
So now we're gonna move on to parallel, okay? So for parallel, let's see, we have a scenario where we have a wall as well, and then it's divided between um we have a layer of wood on the left, let's say on the left, and then um brick on the right. And then we have temperature T2 and then T1, so there are two different temperature. And let's say T2, let's say T2 is larger than T1, so heat is gonna have two, it can travel through two paths, through the wood or to the brick. So heat transfer are gonna be divided through two parts, so these are parallel. And I can make an analogy through physics and circuits as well. Let's move to a different page. So now over here we have a circuit. And so we know we learned in physics that these two resistors are parallel to each other. So when it goes through two resistor with two different resistance, it can have two different currents. So over here it's going to be I1, and then I2, resistor 1, resistor 2. So we know that according to Ohm's law, delta V is equal to IR. So I is equal to delta V over R total. And then we know that junction law, we can know that I is equal to I1 plus I2. And so to get I1 and I2, I1 is equal to delta V over R1 plus delta V over R2, and then I is just delta V over R total. Let's go down here, R total. So when you cross out all of the delta of the voltage change, you can have 1 over R total 1 over R1 plus 1 over R2. So it's essentially the same thing for um, this example up here. So we're gonna have so say Q is equal to what we said earlier, delta T um Q I'm sorry, delta T over is equal to Q times R. So over here we're gonna have um Q is equal to Q1 plus Q2 because over here he is traveling through two different pathways, Q1 Q1 and Q2. So Q1 is equal to um, delta T divided by the resistance of break break over with, and then Q2 is equal to delta T over the resistance of break. So learning from the parallel rule, Q total Q total is gonna be delta T resistance of fluid plus delta T over resistance of break. So Q total we know over here is equal to delta T over R total. So we would have delta T over R total equal to delta T over R wood over delta T over R break. We would have 1 over R total equal to 1 over R wood equal to 1 over R break. And that's how we derive the expression for parallel. Thank you for listening, guys. So now we're gonna work through this example, okay? So we're gonna determine the total resistance of a typical home wall with brick, insulation, studs, and double pane window glass. So we're gonna draw out the scenario. We draw out a window. It's gonna divide it over into two sections. So one's gonna be a window and one's gonna be a non-window. Because this is they install double pane window glass. So over here we would have air, glass one, glass two, and then over here we would have stud, break, insulation. So let us pretend like this over here is room, this one is air, and heat travel down from room temperature to air temperature. So when we look at these structures, we're gonna see that the glass, the window side, the window side, the glass one, glass two in the air, or are in series with each other because air penetrate through them through one layer, and then over non-window, the studs, the brick, and the insulation are in series because air penetrate through, and we can see that the window and the non-window are physically parallel to each other as it goes into two different pathway, but then these are in series. Okay, so wait, what are we gonna do now is we're gonna find the resistance for each individual window versus non-window. So it's gonna do resistance of window. So since window are on series, the total series of the window is just the total resistance of the window is just the sums of resistance of all of the compartments. So we're gonna have over here we have hmm, over here we can have resistance of um, glass one, resistance of convection from the room to the glass one, and then we can have resistance by conduction of glass one, and then we can have resistance of convection of the air between the air and the glass one, and then we can have convection between air and glass two, and then we can have resistance by conduction of glass two, and then finally resistance by convection between glass two and air. Or let's phrase this out, use this term outside. And then now we're gonna do the same for the non-window side. So we can have resistance of non-window. I'm so sorry, my Apple Pencil is just acting up, so sometimes I'm gonna have to interrupt by doing this. Is equal to reduction resistance by convection of the room to the stud, and then we can have a series of conduction of the stud plus our conduction of the break, and then conduction of the insulator, and then our convection of outside and insulator. So the total resistance in this question would just be the total resistance of the window plus the total resistance of non-window. Some of us here might be confused why the total resistance is not like what we know about parallel. It's not the reciprocal of the resistance equal to reciprocal R window plus reciprocal of R non-window. This is because we don't know if we can see that the window and the non-window they have, and like each compartment might have different area. So to be able to use this, we can have they all have to have the same area because um we know that we know that resistance is equal to length over Ka for conduction, and then resistance is equal to 1 over Ha over 2 convection. So to be able to take out the area that we did in part C, the common factor, the area have to be the same for each compartment. Okay, so we don't know that for this case, so that's why we're just gonna have to sum the resistance of the window and the non-window to get the total resistance. Thank you for listening.